The Llama 3 herd of models is a set of AI foundation models developed by Meta for multilinguality, coding, reasoning, and tool usage. The flagship model boasts 405 billion parameters and a context window of up to 128,000 tokens. Despite the development of image, video, and speech extensions, these multimodal models are not yet ready for public use. Llama 3 series encompass three multilingual models, delineated by their parameter sizes: 8B, 70B, 405B. The research paper focuses on the Llama 3.1 models, which adhere to scaling laws and aim for compute optimization within their training budget. The models are grounded on a standard dense transformer architecture with minor modifications to ensure training stability, using procedures like supervised fine-tuning, rejection sampling, and direct preference optimization. Performance evaluations and comparisons display that the Llama 3 models match the effectiveness of competitor models like GPT-4 and even outdo similar parameter models. Specifically, the 405B model reaches state-of-the-art performance levels. All three Llama 3 models are publicly released under the newly updated Llama 3 community license, fostering innovation in AI research. While multimodal models integrating image, video, and speech understanding are in the works, the paper discloses their ongoing evolution without detailing an expected release date. This implies the future extension of the Llama 3 models to embrace more dynamic applications. The document reviews key performance benchmarks of various models, including different versions of the Llama 3 model, 8B, 70B, and 405B parameters, against competitors like GPT 3.5 Turbo, GPT-4, and others. Llama 3 models generally perform competitively across all tasks, with the 405B model frequently achieving the highest scores. Llama 3's architecture is a two-stage process focusing on language model pre- and post-training. The pre-training scales up to involve 15.6 trillion tokens while extending the context window to 128K tokens. The post-training aligns the pre-trained model with human feedback and integrates new capabilities and safety mitigations. The document also details efforts to expand Llama 3's multimodal capabilities, including separate encodings for image and speech based on large dataset training. Cross-attention layers integrate image encodings into the language model without changing its parameters, and speech encodings get converted into token representations compatible with the Llama 3 model. Finally, detailed pre-training efforts are highlighted, including corpus curation, model architecture development, efficiency techniques, and a pre-training recipe, along with stringent data curation and filtering methods to enhance the model's safety and quality. The document notes that the multimodal enhancements are still in their developmental stages. The authors have developed a custom parser to extract high-quality text from web documents, and effectively remove redundant content. Human evaluations and experiments highlight the custom parser's superiority and the negative impact of Markdown on model performance. The deduplication process involves URL, document, and line-level deduplication to ensure diversity. Heuristic and model-based filtering is applied to eliminate low-quality texts, with successful implementation of fast classifiers. Specific data extraction and filtering pipelines are designed for code and mathematical content, as well multilingual data. The authors emphasize language-specific heuristic filtering and model-based filters to ensure high-quality multilingual documents. Performance is optimized through a balanced mix of different data sources. The final data mix comprises around 50% general knowledge tokens, 25% mathematical and reasoning tokens, 17% code tokens, and 8% multilingual tokens. Annealing, a technique reducing the learning rate, is aligned with high-quality mathematical and code data, demonstrating improved performance on key benchmarks. Annealing is also proven efficient to assess the value of small domain-specific datasets. Llama 3 uses a dense transformer architecture like its predecessors, with minor modifications including grouped query attention and attention masking. Various methods and strategies aimed at enhancing data quality, optimizing data mix, and adopting novel techniques, with the focus on data quality, data mix, and annealing boosts the model's robust performance and generalization capabilities. The Llama 3 models feature unique hyperparameters like 32 to 126 layers, Model dimensions between 4096 and 16384. Varying FFN dimensions, and 32, 64, or 128 attention heads. They utilize a 128K token vocabulary, merging the TikToken tokenizer with 28K non-English language tokens, improving compression rates and processing capacity. The rope method is used for positional embeddings with a base frequency of 500,000, supporting longer context lengths. The Llama 3405B model, deeming compute optimal, consists of 126 layers, a token representation dimension of 16,384, and 128 attention heads. The product optimizes the pre-training compute budget through the development of scaling laws for model size and addresses challenges like noisy and unreliable prediction of next token prediction loss and specific benchmark performance. A two-stage method is used to establish a correlation between the compute optimal model's negative log likelihood on downstream tasks and the training flops. Experiments employed a range of models with compute budgets between 6 times 10^18 flops to 10^22 flops, adopting a cosine learning rate schedule with a linear warm-up for 2000 training steps. Isoflops curves, reflecting the relationship between compute budget and validation loss, were utilized to determine the compute optimal models for the respective compute budgets. Such models predicted the optimal number of training tokens for a specific compute budget, forming the base for training a flagship model with 405 billion parameters. In forecasting downstream performance, normalized negative log likelihood of the correct answer, and training flops were used to establish a linear correlation. Infrastructure and optimizations were outlined that enabled efficient large-scale pre-training of the Llama 3 model, securing its training on Meta's production clusters. The page discusses prediction models and the high-tech infrastructure deployed for the ARC Challenge benchmark and Llama 3405B model training. The scaling law graphs are used to predict model performance and optimize training strategies. The Llama 3405B model utilizes an infrastructure consisting of 16,000 H100 GPUs installed on Meta's Grand Teton AI server platform, managed by Meta's Global Training Scheduler, MAST. Meta's distributed file system, Tectonic, provides a robust storage solution, housing 240 petabytes of data across 7,500 SSD-equipped servers, with peak throughputs up to 7 terabytes per second. Extensive efforts are made to optimize the checkpointing process to reduce GPU pause time and augment recovery success. The model benefits from two types of network configurations, ROS fabric and InfiniBand fabric. The former connects 24,000 GPUs over a three-tiered CLO network, while requiring optimization to accommodate a 1:7 oversubscription ratio at the aggregate layer. Traditional load balancing methods are improvised to address higher network flows, leading to increased network efficiency. The report further details the scaling configurations and MFU for the Llama 3405B pre-training, introduces an enhanced ECMP protocol to better distribute network load, and explores the use of a 4D parallelism strategy for efficient model scaling. It also discusses improvements for GPU utilization and pipeline parallelism. Finally, the report suggests future work should focus on refining batch size flexibility and addressing pipeline parallelism imbalances to boost training efficiency. The concept of 4D parallelism categorizes GPUs into tensor parallelism, TP, context parallelism, CP, pipeline parallelism, PP, and data parallelism, DP, groups. GPUs are configured based on their index in the ITH parallelism dimension, determining their groups. To improve pipeline schedules, the authors suggest a modified pipeline schedule enabling the flexible setting of the number of micro-batches per batch. This flexibility helps optimize between depth-first and breadth-first schedules for efficiency. Further efficiency is achieved through an interleaved schedule with V-pipeline stages. Asynchronous communication in PP accelerates training, and the torch_NCCL_avoid_record_streams flag is enabled to reduce memory usage. Proactive tensor deallocation also helps limit memory costs. For improved memory efficiency during training, context parallelism is utilized. The input sequence is split into two *CP chunks, and the CP rank receives two of these for better load balancing. This approach allows for greater flexibility in supporting different attention mask types. To optimize pipeline parallelism, the model partitions pipeline stages across pipeline ranks. Each GPU rank handles two stages. The sequence of micro-batches is denoted using colored blocks, and the number of continuous micro-batches can be tuned for optimization. Parallelism dimensions are also optimized for network communication, with an order chosen to minimize overheads. A memory consumption estimator and performance projection tool assist in identifying inefficient memory configurations and projecting overall training performance. For training stability, FP32 gradient accumulation is used during backward computation. The collective communication library used is based on NVIDIA's NCCL library, though it has undergone enhancements to improve performance. Future work involves deeper changes in NCCLX to tackle inefficiencies holistically. In summary, Llama 3 uses parallelism strategies and communication optimizations to enhance training performance and stability, addressing large-scale model training challenges such as memory efficiency, communication overhead, and load balancing. Unexpected interruptions to the Llama 3405B pre-training phase were mainly due to hardware issues, especially the GPU, which attributed to 78% of cases. Over the 54-day period, a total of 466 interruptions were recorded, primarily from hardware-related problems, and involved 16K GPU training. Nonetheless, over 90% of effective training time was achieved, aided by quick diagnosis tools like PyTorch's built-in NCCL flight recorder. Large-scale training debugging was complex due to the mixed use of NVLink and ROS in the network, with NVLink data transfers often failing without clear error codes. Solutions like NCCLX were critical in diagnosing failures. The report revealed that environmental factors like temperature fluctuations impacted training performance, with the potential to cause a 1–2% variation in throughput. Power fluctuations influenced by simultaneous GPU power consumption also posed challenges to data center power grids. Pre-training the model involved three stages: initial pre-training, long context pre-training, and annealing, with initial batch size set at 4M tokens. Adjustments to the pre-training data mix improved efficiency and results. The long context pre-training helped with larger context windows, starting from 8K to 128K tokens. The project underlined the significance of robust diagnostic tools, system design, environmental considerations, and adaptable training methods for managing large-scale GPU training environments. Figure 7 displays the post-training approach for Llama 3, including rejection sampling, supervised fine-tuning, SFT, and direct preference optimization, DPO. Section 3.4.3 annealing * relates to the last phase of pre-training, where the learning rate is adjusted to 0/40 million tokens with adjustments made to data sourcing, using polyac averaging to determine the final states of the pre-training model. Section 4 post-training * explains human feedback alignment in post-training via SFT and DPO using human or synthetically generated annotations. Strategies for data curation are discussed to promote reasoning, coding, multilingualism, and other capabilities. Section 4.1 Modeling * explores the alignment and fine-tuning processes using a reward model added onto the pre-trained model, illustrated in Figure 7. Section 4.1.1 Chat dialogue format * underscores the necessity for a chat protocol for human-AI interactions, with new capabilities like tool use introduced. The document wraps up with the definition of post-training as any training occurring after the pre-training phase. A multi-message chat protocol was introduced. Special tokens were used to denote message start and end points. Reward modeling involves preference pairs and edited responses, and model fine-tuning is conducted via SFT and DPO. Models are averaged from various experiments to enhance robustness and performance. The page details the refining processes, promoting training efficiency and data optimization. This protocols result in a capable, aligned AI system. Table 6 provides statistics of human preference data across various datasets used in the Llama 3 alignment. This includes general English, coding, multilingual, and reasoning and tools, with measures for dialogue percentage, average dialogue turns, and token counts. The iterative process used for data collection and model training involves 6 rounds of data collection and annotation. Post-training data composition plays a significant role in shaping models. Annotation techniques include rating responses on a 4-level scale and refining preferred responses. Preference annotation statistics reveal an increase in prompt and response lengths for Llama 3. Preference data is employed for reward modeling, while only latest batches are used for direct preference optimization, DPO, training. Responses with significant or better chosen responses are trained, while similar answers are discarded. The sources of supervised fine-tuning, SFT, data include human annotation collections and synthetic data targeting specific capabilities. Other statistics, such as the proportion of examples, dialogue turn counts, and token counts, are outlined in Table 7. Rejection sampling, RS, works by generating multiple outputs for each prompt that are later evaluated. The paged attention mechanism enhances rejection sampling efficiency by improving memory utilization and supporting arbitrary output lengths. To ensure high-quality data, methods like rule-based data removal and modification, and model-based techniques such as topic classification are used. Page 17 discusses data collection, annotation, and post-training processes for Llama 3. The approach combines iterative rounds and quality control measures to refine the model. Future efforts may explore strategies for further data optimization and model alignment. Quality scoring assesses each sample through a reward model, and Llama-based signals, considering top quartile data as high quality. Difficulty scoring uses Instig and Llama-based scoring to rank more complex examples. Semantic deduplication eliminates redundant data through clustering dialogues using Roberta and then applying a selection process within those clusters. This text also focuses on enhancing code capabilities through Llama 3. For code training, a 1T token mix, mostly code data, branches from the main pre-training run. Long context fine-tuning extends the expert's context length to 16K tokens on repo-level code data. To improve code generation, synthetic data generation is used, yielding more than 2.7 million synthetic examples. In synthetic data generation, execution feedback challenges were raised when training the Llama 3405B model on its own generated data. To overcome this, execution feedback was used along with a multi-step procedure involving problem description generation, solution generation, analysis, self-correction, and iterative improvement. In synthetic data generation, programming language translation and back translation, the Llama 3 model is employed to bridge the performance gap existing between different programming languages by translating common languages into less common ones. Back translation is used in case execution feedback is less informative, generating around 1.2 million synthetic dialogues for capabilities like documentation and explanations. These methodologies combinedly enhance model performance for generating diverse programming solutions and help continuously improve the model through iterative fine-tuning processes and error feedback mechanisms. Figures and examples. Figure 8** demonstrates Llama 3's *ability to translate Python code into PHP, showing the model's flexibility in handling diverse programming languages. Figure 9** contrasts code generated with and without system prompts, highlighting the improvements in code quality achieved through system prompts. Key methodologies. **1. Generate. Llama 3 is prompted to generate data that aligns with desired capabilities like code commenting and explaining, using pre-training data from multiple languages. 2. Back translate. The model reconstructs the original code from the synthetically generated descriptive elements, ensuring data accuracy. 3. Filter. The model verifies the back-translated code's accuracy against the original code, selecting only the highest quality examples for the SFT training dataset. System prompt steering. System prompts, used during rejection sampling, enhance code readability, thoroughness, and specificity, playing an important role in model fine-tuning. Filtering training data. The challenge of filtering training data involves dealing with potential bugs in rejection sampled data that contain both code and natural language. Connection to previous sections. The methodologies and techniques discussed here build on concepts introduced in earlier sections, continuing the iterative refinement of the model's capabilities. Limitations and future work. Future efforts may address the challenge of detecting and filtering errors in mixed code and language responses. In conclusion, the page presents strategies for improving Llama 3's code generation, focusing on system prompts, back translation, and rigorous filtering. Model as judge approach. The model as judge approach is used to ensure code correctness and style. This methodology involves earlier versions of Llama 3 judging code based on correctness and style, and retaining only perfect scoring samples. Some challenging examples are revised until they meet the criteria, balancing quality and difficulty. Multilinguality. Llama 3's multilingual abilities are enhanced through training a specialized expert on a large corpus of multilingual data, collecting high-quality multilingual instruction tuning data, and addressing multilingual steering challenges. Expert training. To acquire better human annotations in non-English languages, a multilingual expert model is trained using 90% multilingual tokens. The expert model is then used to collect high-quality annotations in non-English languages. Multilingual data collection. The multilingual SFT data includes human annotations, data from other NLP tasks, rejection sampled data, and translated reasoning data. Methods include collecting human annotated data, rewriting multilingual task data into dialogue format, applying rejection sampling to human annotated prompts, and using translated data for synthetic quantitative reasoning. Conclusion. The methodologies and strategies outlined enhance Llama 3's code evaluation and multilingual capabilities. The model as judge approach ensures high-quality data, while multilingual strategies boost the model's performance in various languages. The multiple processes and considerations discussed are key to the development of a robust, multilingual AI model. Key challenges and methodologies in mathematical reasoning. The main difficulties in mathematical reasoning include scarcity of prompts for supervised fine-tuning, SFT, lack of ground truth chain of thought, inaccuracies in intermediate steps, the need for models to use external tools, and inconsistency between training and inference stages. These challenges can be addressed by converting pre-training data into a question-answer format, utilizing Llama 3 to generate step-by-step solutions and validate their correctness, employing outcome and reward models to filter incorrect reasoning steps, combining textual reasoning and Python code with Llama 3, and using incorrect generations as feedback for model improvement. Context length extension and tool use in Llama 3. Context length in Llama 3 is extended from 8K to 128K tokens. Regressions in long context capabilities arising from naive SFT application are counteracted using synthetic data. Synthetic data generation, which focuses on question answering, summarization, and code reasoning, is performed by earlier Llama 3 versions. Direct preference optimization, DPO, does not detriment long context performance if the SFT model is proficient in long context tasks. Furthermore, Llama 3 is trained to use tools like search engines and Python interpreters, increasing their task-solving range. These methodologies result in an effective and versatile machine learning model capable of high accuracy in complex mathematical reasoning. This section presents the methods used to improve Llama 3's tool usage functions via the Wolfram Alpha API, including the use of Python objects, human annotations, and synthetic data. It explains how datasets and file-type annotations are created to optimize performance. Llama 3's ability to perform complex multi-step processes is depicted in Figure 10. The model is trained to use tools only when necessary, avoiding tool calls for simple queries and refining decision-making around tool use. Llama 3's zero-shot tool use or function calling is improved by fine-tuning it on partly synthetic tuples, including function definitions, user queries, and calls. Function calling is divided into single, nested, and parallel types. to offer diverse functions, queries, and ground truths. Real functions from the stack are utilized to ground synthetic user queries. Function calls, definitions are extracted, cleaned, filtered, and then natural language queries corresponding to calls are generated using Llama 3. For multi-turn function calling, synthetic data is generated in a mechanism similar to Li et al. 2023b, with multiple agents creating domains, APIs, user queries, API calls, and responses. The agents, all versions of Llama 3, collaborate step by step in their specific roles. The challenge of maintaining factuality against hallucinations in large language models is also discussed. Despite recognizing that factuality is broader, the authors adopt a hallucination-first approach. The section offers an in-depth overview of improving Llama 3's tool usage capabilities, ensuring diverse data, and tackling factuality issues. The technique used involves a knowledge-probing method maximizing Llama 3's in-context learning. The alignment data generation process includes data extraction, question generation, response sampling, correctness scoring, informativeness scoring, and refusal generation by Llama 3. The process discourages responses to questions Llama 3 isn't sure about and targets factual inconsistencies or inaccuracies in pre-training data. Additional labeled factuality data collection addresses factually sensitive topics. Figure 11 in the documentation provides a practical application for analyzing and visualizing file uploads by Llama 3. The methodology, which employs the model itself as a judge, is a contrast to traditional external assessment methods. The limitations lie within factually inconsistent or incorrect pre-training data and is an area for possible future enhancement of Llama 3's performance. The page thoroughly explains the technique to align post-training knowledge of a language model, emphasizing factual consistency and self-assessment capabilities. The concept of steerability is discussed in context to Llama 3, with insights into improving steerability through prompts and natural language instructions. It also outlines Llama 3's evaluation, comparing its performance with other models on numerous characteristics like common sense reasoning and reading comprehension. This technical content revolves around the evaluation of Llama 3 models in contrast with other models on different benchmarks. It acknowledges that, due to difficulty in recomputing scores and API constraints, some models, like Llama 3405b, don't report category averages. Statistical significance is assessed considering variables such as random seeds, batch size, and benchmark data selection using a specific analytical formula. Llama 3's 8B and 70B show superior performance across most benchmarks, with 70B showing improvement over its predecessor, Llama 270B, and surpassing Mixtral 8 by 22B. The data provides a granular view of model performances, but variances in experimental setups may affect fair comparisons. Further effort may focus on overcoming these limitations. Llama 3 models perform optimally across reading comprehension tasks, with Llama 370B and 405B notably matching or outperforming competing models. In coding tasks, Llama 370B and 405B demonstrate improved results. Model robustness is evaluated using the MMLU benchmark, concentrating on sensitivity to various design factors including few-shot label bias, label variance, answer order, and prompt format. In conclusion, Llama 3405B shows promising performance, especially in coding tasks, emphasizing the necessity of solid evaluation methodologies to guarantee reliable model output under diverse conditions. The evaluation of AI models on common sense understanding, math and reasoning, and general language tasks reveals Llama 3405B's outstanding performance in common sense QA, PIQA, MMLU, and BB Hard. Mixtral 8 to 22B and Llama 370B's strong performance in PIQA and Winagrande, and GPT-4's leading performance in GSM-8K and ARC-C. Nemotron 4340B excels in Winagrande. In general, larger models like Llama 3405B and GPT-4 outperform smaller models, suggesting a correlation between model size and performance. The performance fluctuations suggest areas for optimization and future improvement. In label variants, rarer and common tokens and canonical and numerical labels are examined to test the model's generalization across different representations. The order stability of model performance across different answer orders is evaluated based on Wang et al.'s 2024 methodology. The performance variation across different task prompts tests how varying information levels in prompts affect model performance. Robustness tests reveal Llama 3 model's outstanding stability across different multiple-choice question, MCQ, labels, answer orders, and prompt formats despite variations in input representation. Future research can explore the impact of more complex or less structured prompts and robustness across diverse tasks and datasets. Adversarial benchmarks. The model's robustness is tested using challenging adversarial benchmarks, Adversarial Squad, Dynabench Squad, GSM+, and PAWS, covering question answering, mathematical reasoning, and paraphrase detection tasks. Figure 15 contrasts adversarial and non-adversarial scores for Llama 3 models with varying parameters, both pre- and post-training. Paraphrase detection displays resilience against PT and PA adversarial conditions, while mathematical reasoning and question answering have lower performance on adversarial benchmarks. Contamination analysis. The contamination analysis estimates how much benchmark scores are influenced by evaluation data in the pre-training corpus. This area remains open due to false positives and negatives in the methods used. It follows recommendations from Singh et al., 2024. Performance on long context tasks. Table 14 discloses performance metrics for pre-trained Llama 3 models on long context tasks like quality and GSM-8K, with their 95% confidence intervals. Contamination and performance gain estimation. Table 15 outlines contamination levels and estimated performance gains in various evaluation datasets, using an 8-gram overlap method founded on Singh et al., 2024. The performance benefits from contamination vary widely across datasets. Methodology for contamination detection. The 8-gram overlap method is used to detect contamination by contrasting, clean, and entire datasets, and selecting contamination thresholds, TD, to maximize significant performance gains. Results and analysis and post-trained language model evaluation. The analysis reveals varying impacts of contamination on performance across datasets, and post-training data is decontaminated using exact match techniques. Experimental setup and conclusion. The experimental setup for post-training echoes pre-training procedures, emphasizing independent evaluations of other models to ensure fair comparison. Contamination variability necessitates specific detection methods for different datasets. Rigorous post-training evaluations ensure the result's robustness. The article outlines an evaluation framework for Llama 3 models using several benchmarks. General knowledge benchmarks, like MMLU and MMLU Pro, have shown the 8B and 70B Llama 3 variants outperforming other similar-sized models. The instruction following capability assessment, IF eval, also indicates Llama 3's superiority. The Llama 3 models are also evaluated on proficiency exams, including GRE, LSAT, SAT, AP, and GMAT, with GRE answers being marked correct if all correct options are selected. Results show these models performing well, suggesting advanced capabilities. These models also underwent code generation tasks using Python and multi-programming language benchmarks. The evaluation is based on the pass at n metric, which assesses the pass rate for a set of unit tests among n generations. Llama 3 8B and 70B models excelled in Python benchmarks. Despite not discussing limitations explicitly, the article insinuated that the Llama 3 models could be further improved in terms of robustness and accuracy. Overall, Llama 3 models demonstrated strong performance across various domains, proving valuable for stakeholders and researchers studying these advanced large language models. This page evaluates the performance of Llama 3 models, among others, on various tasks. In code generation benchmarks, Human Eval Plus, and MBPP, Llama 3405B and GPT-4o offer the highest performance, with model size correlating strongly with code generation ability. Non-Python code generation sees a drop in performance across models, suggesting a challenge in multi-language code generation. Llama 3 supports multi-language code generation across 8 languages, assessed via multilingual MMLU and multilingual grade school math (MGSM) benchmarks. Llama 3405B excels at MGSM but slightly trails GPT-4o in multilingual MMLU. The models have not been optimized for languages beyond these 8, requiring further fine-tuning for additional languages. Models were evaluated on math and reasoning benchmarks, with Llama 3.8B and 70B outperforming others of similar size on GSM-8K, math, and GPQA tasks. On complex tasks relying on extracting information from long texts, Llama 3 models performed near perfectly on the needle in a haystack and zero scrolls tasks and outperformed others on the infinite bench task. On zero-shot tool use tasks, Nexus, API Bank, Gorilla API Bench, BFCL, Llama 3 models led Nexus performance, and matched or surpassed others on API Bank and BFCL tasks. Overall, Llama 3 models, particularly 405B variant, displayed superior performance across diverse tasks, underlining advancements in multilingual understanding, mathematical reasoning, long context comprehension, and tool use capabilities. However, multi-language code generation presents a significant room for improvement. Other models like GPT-4o and Claude 3.5 Sonnet also showed strong performance in certain tasks. The text discusses long context benchmarks including zero scrolls, quality, Casper, S-quality, N, QA, N, MC, and multi-needle, ranking AI models based on metrics like exact match, F1 score, Rouge L etc. The study shows that Llama 3 AI models, particularly the 405B variant, perform well across these benchmarks, with larger models proving particularly adept at long context tasks. Furthermore, it presents human evaluations focused on measuring nuanced model performance aspects, such as tone and cultural context understanding, through code execution tasks, using user prompts drawn from various datasets. Zero-shot tool use benchmarks are also presented, reporting function calling accuracy across multiple platforms. Llama 3405B outperforms other models in several areas, but it falls short of GPT-4o in file upload tasks. The text details the methodology of collecting high-quality prompts for human evaluations, which involved a taxonomy encompassing a wide range of model capabilities and difficulty levels. Finally, the document discusses the human evaluation of different AI models, stressing Llama 3405B's competitiveness. It also acknowledges potential biases in human evaluations while emphasizing the safety measures implemented during the model's development. The text provides a detailed overview of the safety evaluation framework used for the Llama 3 model. It explains human evaluation results demonstrating Llama 3's performance against GPT-4, GPT-4o, and Claude 3.5 Sonnet using 95% confidence intervals. It discusses the concept of uplift or additional risks introduced by AI advancements, and highlights the importance of red teaming for systematic risk identification and mitigation. The text endorses system-level safety mechanisms and outlines benchmark construction using human-written prompts. The vital role of implementing safety measures in the earliest stages of development, known as safety pre-training, is emphasized. The page presents adversarial prompts to evaluate the model's robustness in various contexts, discusses verbatim memorization rates of Llama models, providing data for specific scenarios in Table 24, and introduces safety fine-tuning to mitigate risks associated with AI capabilities. The technique uses metrics including violation rate and false refusal rate, while ensuring improvements don't affect model utility. The text acknowledges limitations of the current analysis but affirms the effectiveness of safety fine-tuning in reducing risks. Lastly, two tables are listed, Table 23 and Table 24, providing examples of adversarial prompts and memorization rates, respectively. The article first discusses the impact of model size on violation rate, VR, and false refusal rate, FRR, indicating larger models, 70B, are superior at distinguishing between adversarial and borderline contexts compared to smaller models, 8B. The quality of safety training data is stressed over its quantity, with AI-assisted annotation tools used to improve data consistency. The use of borderline prompts further assists in reducing FRR. To improve training data, synthetic data generation techniques, including in-context learning and rainbow teaming, are employed for diverse adversarial examples. Next, the process of safety supervised fine-tuning, SFT, is outlined, which uses a strategic balance of helpfulness and safety data, focusing on borderline examples for challenging risk areas. The use of adversarial and borderline examples in preference datasets in DPO further bolsters safety learning. The ratio of these examples and model size greatly influence learning outcomes, highlighting the need for a model-specific safety mix. Finally, figures 19 and 20 support this with comparisons of VR and FRR for Llama 3405B against competitor models across various languages and use case scenarios. Llama 3405B is shown to achieve competitive VR metrics while maintaining a low FRR, illustrating an effective balance of safety and utility. The multilingual safety section emphasizes that safety knowledge doesn't easily translate across languages. The text concludes by admitting that benchmarks are internal to Meta, thus not externally reproducible, and competitor confidentiality is maintained. Overall, the article comprehensively evaluates Llama 3405B model's safety performance, balancing VR and FRR, and the complexities of multilingual safety. Summarized technical content. The violation rate, VR, and false refusal rate, FRR, are key metrics used to assess safety performance of models. Models like Llama 3 focus on balancing these, as opposed to only optimizing one. The quality and distribution of safety data per language notably influence model performance. An iterative method incorporating adversarial and borderline data is used to balance FRR and VR. Llama 3 models demonstrate superior safety with competitive FRR in comparison to other models. To mitigate many-shot jailbreaking attacks on long-context models, Llama 3 employs fine-tuning on SFT datasets and develops a scalable mitigation strategy. Performance is assessed via DOCQA and many-shot benchmarks methodologies, with Llama 3 outperforming competitors. Notable introductions are the scalable mitigation strategy for long-context safety and a balancing routine for FRR and VR. Future work may focus on refining balance between VR and FRR and exploring mitigation strategies. For tool safety, Llama 405B showed significant safety but with a higher rate of false refusals. Cybersecurity evaluation of Llama 3 using the CyberSec eval framework revealed that larger models generated more insecure code but with better language quality. They were vulnerable to executing malicious code and susceptible to prompt injection attacks. Llama 3 underperformed in identifying vulnerabilities compared to non-LLM tools. The model had moderate persuasive capability in spear phishing attempts, but failed as an autonomous agent in ransomware attacks. An Uplift study also evaluated its impact on cyberattack success rates. Despite its strengths, the model showed limitations in high false refusal rates and vulnerability to certain attacks. Future plans include improving robustness against vulnerabilities and enhancing performance in cybersecurity tasks. The text explores various prompt injection techniques like repeated token attacks and information overload utilized in manipulating the output of large language models, LLMs, such as Llama 3, Mixtral, Gemini Pro, and GPT-4 Turbo, revealing Llama 3 models are generally more vulnerable to these attacks. It also assesses how convincingly different models generate spear phishing attempts, with Llama 3 apparently producing more persuasive attempts. The paper presents a cybersecurity challenge assessing the LLM's utility in assisting users, revealing that the LLM does not significantly enhance the challenge's completion rates. Furthermore, it addresses uplift testing for ILM's potential risk in planning chemical and biological attacks. In a controlled study with expert reviews, no significant performance uptick was seen due to the use of Llama 3 models, indicating a low risk of these models significantly improving the planning capabilities for such attacks. In closing, while LLMs like Llama 3 can be exploited through prompt injection attacks, their usefulness in fostering harmful activities like spear phishing or strategizing chemical and biological attacks is minimal. The text discusses the application of red teaming to recognize and neutralize risks tied to the release of Llama 3 models, mainly for misuse in biological or chemical weapon attacks. This involves adversarial testing methodologies and findings, along with challenges introduced by multilingual contexts, aiming to enhance model safety via iterative testing and expert collaboration. The text discusses adversarial techniques in LLMs including unsafe tool chaining, forced tool use, and modifying tool use parameters. Child safety risk assessments have been performed using dedicated experts and objective-based methodologies. In terms of system-level safety, a safety-optimized classifier called Llama Guard 3 was created, which operates on 13 hazard categories and leans on prompts to increase unsafe responses within the training set. This new model significantly curtails potential threat, delivering an average violation reduction of 65% across benchmarks. The text explores violation and false refusal trade-offs, evidenced in Table 25, and offers Llama Guard 3's flexibility to tailor specific harm parameters. The system facilitates deployment by using int8 quantization, reducing its size by more than 40% without compromising performance. New system safeguards are discussed: Prompt Guard, detecting prompt attacks, and Code Shield, focusing on detecting insecure code generation. The text underlines that careful balancing of reducing harm and managing false refusals are key to the Llama Guard 3 system. It underscores the significance of new tools such as Prompt Guard and Code Shield in advancing LLM safety and facilitating responsible AI deployment. The documentation presents performance metrics and details for Llama Guard 3's application on the Llama 3 model, along with its limitations and inference techniques. The full Llama Guard configuration indicates an increase in false refusal rate, FRR, and a significant decrease in violation rate, VR, across many categories. However, the violation rate rises for the category indiscriminate weapons. The analysis of int8 quantization shows high precision in recall, minimal effect from quantization on English capability, and improved false positive rate, FPR, for tool use capability. The limitations section discusses potential risks like harmful content generation, especially in non-English languages, risks of adversarial attacks, and the need for ongoing research. Two main methods to enhance inference efficiency, namely pipeline parallelism and FP8 quantization, are discussed. The system proved robust in reducing violation rates but needs constant updates for safety. Metrics for Prompt Guard show high true positive rates, TPRs, and relatively low false positive rates, FPRs, indicating excellent performance. The document also explores micro-batching for inference, positively affecting throughput. The FP8 quantization section details experiments using native FP8 support for low-precision inference needs. It specifies no quantization is performed in the first and last transformer layers due to sensitivity. Future work may focus on fine-tuning and exploring the applicability of these techniques to other models and tasks. The document highlights the superiority of row-wise FP8 quantization over tensor-wise version, owing to its greater granularity and precise adjustments. A major concern addressed is the impact of quantization errors on model responses, which can be controlled by placing an upper limit of 1200 on dynamic scaling factors. An analysis of reward model scores for FP8 and BF16 demonstrates that FP8 quantization has a negligible effect on models' responses, attesting to its robustness. Further, an experimental assessment reveals that FP8 inference achieves a 50% boost in throughput during prefill stage and offers a better throughput latency trade-off in decoding than a two-machine BF16 approach. The focus then purports to integrating visual recognition into Llama 3 using a compositional methodology comprising two stages. First, integrating a pre-trained image encoder with a pre-trained language model using a large dataset of image-text pairs. And second, introducing temporal aggregator and video cross-attention layers for video processing. The method ensures parallelism in vision and language modeling, simplifies joint pre-training process, maintains performance in text-only tasks, and enhances efficiency by avoiding passing of full-resolution images through language models networks. However, these multimodal models are still in development. The discussion then details methodologies and data used for training visual recognition, focusing on image and video data. The data processing involves quality filtering, perceptual deduplication, implied resampling and optical character recognition, besides safety mitigations throughout the pipeline for data integrity. The paper thus delves into the advantages of the proposed FP8 quantization method and the strategy and processes for incorporating visual recognition into Llama 3. The text discusses enhancing the multimodal capabilities of the Llama 3 model. The techniques employed include data deduplication via SSCD model, enhancing diversity via resampling strategy, boosting OCR capabilities, and rendering document pages as images attached with their respective text. These strategies address various tasks, promoting efficiency and diversity in training data. The authors also emphasize ensuring the pre-training dataset does not contain inappropriate content. In terms of data filtering and augmentation, the training set excludes unsafe content, uses face blurring to protect privacy, and creates an annealed dataset using resampling with n-grams. Additional data from various sources are also added. This includes visual grounding, screenshot parsing, question-answer pairs, synthetic captions, and synthetically generated structured images. For video data pre-training, a curated dataset of video text pairs is created, which undergoes text filtering, alignment filtering, and meets certain dataset characteristics in terms of video duration, spatial resolution, and aspect ratio. The model architecture comprises of an image encoder, a vision transformer, VIT. In conclusion, the text outlines the data filtering and augmentation strategies for the training data, detailing pre-processing steps for video data, and introducing the model architecture. These methodologies focus on data quality, safety and are integral to developing a robust visual recognition model. The authors use a multi-layer feature extraction approach and include 8 gated self-attention layers for image encoding, using a transformed block-based strategy. The image adapter uses cross-attention layers, employing generalized query attention for better performance, with the Llama 3 model's cross-attention introducing around 100 billion parameters. The video adapter can process up to 64 video frames, using a temporal aggregator for modeling temporal structure. The research also deals with challenges posed by model and data heterogeneity in large models through efficient data and tensor parallelization strategies, with pipeline parallelization additionally used for the 405 billion parameter model. Image token processing requirements are balanced with text token computations through sequence parallelization in the image encoder and larger micro-batch sizes for texts. Numerical instabilities from integrating image encoding are addressed by switching to FP32 precision for gradient accumulation. Pre-training includes the use of pre-trained text model and vision encoder weights, with iterative adjustments made based on learned insights. Image processing involves 6 billion image text pairs and an annealing dataset. Video pre-training builds on these weights and uses similar hyperparameters with minor amendments. The post-training phase fine-tunes the model using curated conversational data and optimization techniques, followed by a quality tuning stage to enhance evaluation performance. For image capabilities, the supervised fine-tuning process employs academic datasets and human annotations for increased diversity and quality. The methodologies address data disparity, computational instabilities, and provide detailed pre- and post-training processes for enhancing multimodal capabilities. The paper showcases human-in-the-loop annotations, which provide annotators with machine learning model outputs to refine, improving both the quantity and quality of annotations. It discusses the generation of synthetic multimodal data via text representations of images using large language models, LLMs, and converting this text data into images or composite tables and charts, thus creating more conversational data. Video data annotation emphasizes understanding multiple frames instead of a single frame. Techniques for supervised fine-tuning, SFT, for images and videos are described, which involve pre-trained models, weight averaging of top-ranked models, and certain initialization and fine-tuning specifics. Preference datasets for reward modeling are created through human annotations and synthetic data, where model outputs are compared and labeled as chosen or rejected. Rejection sampling is utilized to produce on-policy negative samples, improving model robustness. In reward modeling, the vision reward model is trained on a vision SFT model and a language model, while direct preference optimization, DPO, further trains vision adapters using preference data. Regular updating in an exponential moving average fashion enhances learning and performance. Rejection sampling is used for reasoning tasks to generate multiple answers based on system prompts. High-quality answers are selected for retraining, improving the model's performance over time. Quality tuning ultimately improves the overall quality of the model's responses by leveraging a highly curated SFT dataset for training. In essence, the document underscores the role of iterative sampling and strategic updates in optimizing model performance. The Llama 3 model has been evaluated for image and video recognition abilities using diverse datasets. Image understanding was tested with datasets like MMMU, VQA-V2, AI2 diagram, Chart-QA, Text-VQA, and DOC-VQA, assessing multimodal reasoning, language understanding, chart comprehension and OCR abilities. Performance comparison with Gemini and X.AI models suggested Llama 3 outperformed GPT-4v in all benchmarks, but trailed Gemini 1.5 Pro and Claude 3.5 Sonnet, especially excelling in document understanding tasks. Video recognition was evaluated by perception test focusing on temporal reasoning questions. The model displayed versatile skills in memory, abstraction, physics, semantics, and various types of reasoning associated with videos worldwide. The Llama 3 V405B model demonstrated competitive performance across image recognition benchmarks, displayed strength in document understanding tasks and in temporal reasoning. Fields for improvement include matching or surpassing leading models like Gemini 1.5 Pro and Claude 3.5 Sonnet. Additionally, video understanding capabilities were evaluated using benchmarks including Perception Test, TVQA, NextQA, and ActivityNet-QA. They highlight the model's strong performance in complex temporal reasoning, compositional reasoning, temporal and causal reasoning, and long video clip understanding. The model's limitations include reliance on zero-shot evaluation and limited frame processing, suggesting potential for enhancement. Overall, the Llama 3 models demonstrated effective and competitive video understanding capabilities in zero-shot settings. The speech generation module utilizes a streaming text-to-speech (TTS) system for real-time speech waveforms generation based on language model decoding. The Llama 3 model uses 15 million hours of unlabeled speech data for pre-training, filtered via a voice activity detection model. Personally identifiable information is removed using the Presidio analyzer. Additionally, supervised fine-tuning employs 230,000 hours of transcribed speech in 34 languages for automatic speech recognition, ASR, training and 90,000 hours of translations for automatic speech translation, AST, data. Synthetic dialogue data is used for fine-tuning the speech adapter across a broad range of languages. Further, 60,000 hours of speech datasets and 25,000 hours of synthetic data are leveraged to generate synthetic data for automatic speech recognition, ASR. Text normalization, TN, and prosody model, PM, are facilitated by training models on datasets of 55,000 and 50,000 hours respectively. Llama 3 embeddings from the 16th decoder layer assist in the training of TN and PM modules. The speech module consists of a speech encoder and an adapter, integrating speech and text tokens directly. The speech encoder, a conformer model, and the speech adapter with approximately 100 million parameters, form the main components of the architecture that handle speech data, ultimately enhancing the language model's capabilities. Speech generation. Text normalization, TN transforms written text to spoken form using an LSTM-based model and Llama 3 embeddings, enhancing semantic accuracy. For instance, 123 could be read differently based on context. This module enables real-time input-output processing which improves speed and precision. Prosody modeling, PM enhances naturalness and expressiveness in synthesized speech. It uses a transformer-based model and incorporates Llama 3 embeddings to predict key prosodic features, phone duration, fundamental frequency, and power average across phone duration. The architecture includes a unidirectional transformer, cross-attention layers, and dual fully connected layers. Training recipe for speech understanding. Speech pre-training. The speech module is trained in 2 stages. Pre-training uses in-labeled data to develop a speech encoder that functions well across languages and acoustic conditions. This is followed by supervised fine-tuning where the adapter and encoder are jointly trained with the language model, using labeled data to improve speech understanding. Multilingual OSR and AST modeling. Mitigating language confusion in multilingual OSR and AST can degrade the model's generality and zero-shot performance. To address this, system prompts indicate only the language of the text output, target side. This strategy potentially enables the model to handle code-switched speech. Speech pre-training algorithm. The pre-training uses the best RQ algorithm designed to enhance cross-language and acoustic capabilities. This also provides a robust foundation for subsequent supervised fine-tuning. Pre-training and supervised fine-tuning. Pre-training. Masking, feature quantization, and 500K training steps are part of pre-training. It uses 16 codebooks for stability, with the projection matrix and codebooks randomly initialized and not updated during training. Supervised fine-tuning. Jointly optimizes the pre-trained speech encoder, a randomly initialized adapter, and Llama 3. The OSR, AST, and spoken dialogue data is used for training. Speech generation. Real-time processing. Employing a look-ahead mechanism and a dynamic alignment strategy ensures low-latency speech synthesis and smooth streaming. Training uses a batch size of 1024 utterances, AtomW optimizer, and a learning rate of 9 × 10⁻⁻⁴ over 1 million updates. Inference. The same training mechanisms are employed during inference for consistency. A delayed pattern approach enhances long-range prosodic dependencies, contributing to the naturalness and expressiveness of synthesized speech. Speech understanding results. Evaluation tasks. The speech interface for Llama 3 is evaluated on OSR, speech translation, and spoken question answering tasks. Performances are compared with Whisper, Seamless M4T, and Gemini models. Evaluations are conducted on English datasets with the word error rate measured. Summary. This page details techniques for pre-training, fine-tuning, and evaluation of a speech processing model integrated with the Llama 3 framework. Innovations include feature quantization with multiple codebooks, a dynamic alignment strategy for speech generation, and a delayed pattern approach for prosody prediction. The evaluation indicates competitive performance against state-of-the-art benchmarks. Automatic speech recognition, OSR, Llama 3's word error rate, WER, on several OSR benchmarks, including MLS, English, Libre Speech, Test Other, Vox Populi, English, and FLIR, 34 languages, are shown to outdo specialized models like Whisper and Seamless M4T. It also equals Gemini's performance on MLS English. Speech translation. Llama 3 presents competitive BLEU scores on the FLIR and Covost 2 datasets for speech translation tasks, again surpassing Whisper and Seamless M4T. This highlights the strength of multimodal foundation models like Llama 3 in complex tasks. Spoken question answering. Llama 3 showcases commendable abilities in spoken question answering, even with code-switched speech. It provides coherent multi-turn dialogue despite its training on single-turn dialogues. Safety evaluation. Using the multilingual MuTox dataset, Llama 3 is proven safe, showing the lowest percentage of added toxicity for English, at less than 1%, and it actively decreases toxicity in outputs. This contrasts Gemini 1.5 Pro, which had numerous empty responses. Speech generation results. Llama 3 evaluations on token-wise input streaming models for speech generation tasks were briefly mentioned, but details were not furnished. Limitations and assumptions. The paper makes certain assumptions for its evaluations and uses averages for unreported language data. Also, for CoVost 2, only 15 of the 21 languages were assessed. Conclusion. Page 67 outlines Llama 3's unique capabilities in various speech-related tasks. It surpasses specialized models in complex, multilingual, and multi-turn interactions, underlining its safety features and toxicity reduction abilities. The comparisons and evaluation results advocate for the superiority of Llama 3 in speech interface abilities, text normalization, and prosody modeling. The article evaluates the Llama 3.8b prosody model, praising its superior naturalness and expressiveness in synthesized speech. It reviews the model's growth, scaling, efficiency, architectural choices, and its alignment with human feedback post-training. Llama 3's multimodal capabilities include image recognition, built on previous research and utilizing contrastive learning to achieve comparable performance to high-end models like Gemini 1.0 Ultra and GPT-4 Vision. The model also supports video inputs, enabling tasks like video-based question answering and reasoning by aligning video and language representations. Unlike other models, Llama 3 avoids fine-tuning the language model for speech tasks to prevent conflicts with non-speech tasks, achieving robust performance at larger scales. The paper emphasizes that groundwork models like Llama 3 are still under development, highlighting the importance of quality data, scale, and simplicity. Despite exploring complex architectures and training methods, simpler approaches were found more beneficial. Organizational strategies were key to Llama 3's development, such as dividing tasks between teams to avoid overfitting and maintaining trustworthiness through independent human evaluations. The authors share their findings to inform research on developing groundwork models and stimulate public debate. Experiments with multimodal capabilities are disclosed as a means to advance research, even though these models remain under development. The article acknowledges the ongoing evolution of multimodal models, using organizational decisions and methods employed in Llama 3's development as a potential guide for future research. The page offers a comprehensive view of Llama 3's multimodal capabilities, development strategy, and its implications for future groundwork models. The public release of Llama 3 is driven by successful safety analyses done throughout the study, including testing for biases, robustness, and misuse scenarios. This ensures model safety and promotes transparency, crucial for responsible development of foundation models, a stepping stone to more advanced AI systems, like AGI. The authors highlight the need for public access to foundational models as an imperative for responsible AI evolution. By releasing Llama 3, they encourage an open and accountable approach to AGI development, which is anticipated to boost innovation by enabling community-based model improvements and safety checks. The release aims to inspire similar practices across the AI industry, fostering a collaborative, transparent environment for the development of safer, more efficient AI systems. In essence, public release of Llama 3 symbolizes advancement of AI development while ensuring safety via community scrutiny, setting a new standard for AGI development practices in the industry.